Let's do an example of Gauss-Jordan inversion. So I mentioned in the discussion of Gauss-Jordan that it is exactly the same algorithm. So I thought it'd be kind of fun to take the actual Gauss-Jordan solution algorithm provided by the book and just modify it to do Gauss-Jordan inversion, which we don't even need to change the name. So the function we're going to input, this is following example 414 in your textbook. I won't recite the coefficients because that just gets annoying. That's the A matrix. Just going for the inverse of it, so we don't need the solution. In fact, we do need a solution. In this case, we need an identity matrix of size 3, because that is the solution to the inversion mechanism we need. So if I can reference back to the textbook to show you what we are doing, we are solving that equation setup. We have a matrix of coefficients, we have a matrix of answers, and that is equivalent to diagonal I. So we're going to solve for that. We have an equation Gauss-Jordan, and we're going to send it the inputs A and B, the coefficient matrix, solution matrix, and press enter, and it's going to give us the inverted matrix, right? No, not quite. So somewhere in this code, it is making the assumption that the output is going to be a single column. Notice that, so you kind of go from the top down and hope everything's okay on your first perusal. You can get very detailed, but let's go a little bit faster than we should initially. So AB is the concatenation of both the entries, so they didn't limit the number of columns there. R and C is the size of A and B, so that should report the actual big R and C. In fact, if you want to uncomment that and run this code again, you can actually see that, yeah, R is three rows, 6 columns. So at that point, it's actually concatenated our matrices appropriately. For J equals 1 to R, so that's doing a for loop over all the rows we have, not limiting anything. At this point, it's just doing row operations to sort them in terms of largest pivot element. And then if it exists, it's sorting by largest pivot element. So really, it's just pure row ops. And look, they're doing it for all of the columns in each one of these circumstances. So nothing inside of these sections, the pivoting section, is going to eliminate the columns of interest. Okay, so AB of J all columns equals AB of J all columns divided by AB of JJ. Notice this is still inside the parent loop. Those are the remaining ifs and fors afterwards, so this is actually existing inside of the for loop started, if I can find the pairing, yeah, all the way up here in line 12. All in one big loop. So for each row, it's basically saying that all of the columns are going to be equal to, no, for a particular row, yeah, all the different columns in the row are equal to AB of J, the columns themselves, divided by the diagonal element. So that is normalization of that one diagonal piece. Now you do the loop where in Gauss-Jordan you start scaling the other row operations and subtracting them from themselves to generate the zeros in the column of interest. So that's pure Gauss. Notice they did the check. If I is not equal to J, if you're not on the diagonal one, then you're good to go. So nothing in all of that was terribly limiting in the number of columns taken into consideration, because that's all columns. This is written for all columns. It's not until we get to the output that you see what's actually causing the issue. So the output they expect is X is AB all rows column C. Now the variable C is defined all the way up here as the total size of AB, so that contains a scalar, a number. So this is going to be the last column on the right hand side, which makes sense if you're expecting a vector output, but let's look at just what AB contains at the very end. So I'll erase the indices. This will feed out the whole matrix AB after all of the row operations have been done. And look, we have the identity matrix on the left side now with coefficients on the right. Now if you don't see what's going on here, this is actually an array, a matrix, whatever you want to call it, wrapped around 2 rows. So columns 1 through 5 fit on the first row, 6 is on the second. It's kind of annoying in MATLAB. After looking at these for a little while, you hardly even see it anymore. Let's do short. See if that helps the legibility of the output any. Hey, it did. Okay, so that's what it looks like when it's not wrapped around columns. Identity matrix on the left, coefficient matrix on the right. is what it is. So that coefficient matrix on the right, the rightmost 3 by 3, that's your inverse. So all we need to do here is, instead of telling the code to only output the rightmost row, let's have it output an answer of the size of b. So that way we have one Gauss-Jordan function that will work simultaneously for vector solutions as well as inversion. Because when you're inverting, you would assumedly input an I matrix B of the same size of A. So in this case, we only want to select AB, all rows. Yeah, the columns are where we're going to be interesting here. So let's do the range of columns from size of A. So as a feed into the A coefficient matrix in dimension 1. So 2 inputs to the size function makes it so that it only feeds out one number. This will be essentially measuring the, well, actually it should be squared all the time, but I think the second is what we actually want, because that's the number of columns in A. So size of A, so the number of columns in A plus 1, because we want it to start in the 4th column. We don't want it to include the 3rd column at all. So size of A plus 1, let's actually put that in parentheses just so we know it's a number. So it's going to be a range. So we're doing all rows of AB, and we're going to do a range from column 4 to column C. Actually, C was already defined for us. That's the maximum number of columns in concatenated matrix AB. So that should do it, right? Did I break it? Let's see how broken it is. Not at all. That's the inverse. Let's check it. A, that's the original matrix, A to the negative 1. That's the inverse matrix, Gauss-Jordan. Oops, I erased the comparison I wanted. Do those match? That's the Gauss-Jordan answer right here. That is the MATLAB built-in inverse answer right there. Hey, look at that. So we now have one Gauss-Jordan function that can both solve matrix problems as well as find the inverse of a matrix for you. There's a reason I like Gauss-Jordan. The code, if you took out some comments, and if you note that really a lot of this is just pivoting. It's massively simple. Gauss-Jordan is just elegant. I like it, unashamedly. But for good reason. It's a nice piece of code, and it does multiple things for you, so use it.